Welcome everyone to our critical design review on our project called C.A.P.E.R. This is our team consisting of 3 electrical engineers. My name is Sarah, alongside with Kellen and William, and we have 1 computer engineer named Paco. Our project is on C.A.P.E.R, an acronym for Compact Animated Parrot with Enhanced Responsiveness. This is a parrot robot that fuses artificial intelligence with animatronics to create lifelike motions with the head, beak, body, tail, and wing flap, as well as voice response capabilities where C.A.P.E.R will actually talk to the person speaking to it. Traditional animatronics are becoming outdated, and the new ones are expensive to produce and install. The next generation of entertainment-oriented robots will require the newest technology for any chance to succeed. The downside to this is the high cost of production and installation of modern animatronics. It would cost companies hundreds and thousands of dollars to upgrade their facilities and accommodate these new figures, and many companies cannot foot the bill. Most current-day entertainment robots are massive, think Disney, and thus are typically bolted to one spot for life. They are also unresponsive, and with C.A.P.E.R, we plan to change that. This is our motivation for C.A.P.E.R, to create a low-cost, low-profile, portable robotic robot suitable for installation in facilities with a smaller economic footprint. Our goal is to ultimately improve human interaction with C.A.P.E.R and to create an affordable and portable entertainment robot in comparison to existing robots that has smooth movement and conversational capabilities. It should also be easy to use and switch between the various input modes with a quick response time of within seconds. C.A.P.E.R integrates modern AI and movement control systems for improved human interaction, being able to carry out simple conversations with the user. Voice activation and speech detection will prompt the AI program to generate appropriate movement and audio data in real time. The raw electrical movement impulses will be translated into motion and synchronized with the audio. It will look like you're actually talking to a parrot. There is also the option of traditional control methods, real-time manual movement control, and pre-recorded sequencing. Our objective is to develop user-friendly interfaces that don't require specialized knowledge to appeal to a wider audience. Simplifying the design and material will also reduce development, installation, and maintenance costs to make it a viable option for smaller venues, schools, and hobbyists. The C.A.P.E.R project is a response to the growing need for ethical and positive application of robots, aimed at moving away from potential negative uses like weaponization and job displacement, and instead move towards entertainment-based practical effects to once again stimulate interest in the field of animatronics while implementing AI technology. These are our specifications. For our demoed specs, we chose to have a response time to user input of within 2 seconds, an 80% accuracy for voice recognition to its own name, and an 80% accuracy for audio response in a realistic manner with intelligible speech. C.A.P.E.R's cornerstone component group will be the robotic Parrot apparatus that is operated by the control system, referred to as the main body. The main body will contain all of the systems needed to turn the signals from the control unit into movement. C.A.P.E.R stands at approximately 2 feet tall, with the frame itself being at around 1.5 feet. The internal central frame is made from wood and will support all of the functional mechanical devices. The internal shaping framework is made from foam, rubber tubing, and thick wiring, and the solenoids are there to react to the signals given from the controller to move the corresponding body part. This is the physical model of the internal central frame. In the photo, you can see the dimensions of each component. As mentioned earlier, C.A.P.E.R will showcase 4 movements: the beak opening and closing, the vertical head tilt, the vertical body tilt, and the lateral tail and wing flap. Each movement will be carried out electrically, but without the use of ultra-precise position or speed monitoring. The binary on-off style of movement control makes programming more timely, efficient, and understandable, without jeopardizing the realism of the movement. The figure will stand upright, fixed atop a pedestal for permanent mounting, and wires will run out the bottom of the figure for connection to a separate control unit. Here is a physical showing of the movements. All of the movements are rigid with the exception of the wings, which puff out when the tail moves due to them being connected to the same solenoid. The operation modes C.A.P.E.R will employ are the fully manual live operation, partial manual live operation, and pre-recorded sequence operation. The fully manual live operation uses parallel digital inputs so C.A.P.E.R can be manually operated using push buttons. C.A.P.E.R features 4 movements, and therefore there will be 4 buttons. Pressing a button will activate the corresponding joint movement, and depressing the button will return that joint to its resting state. In this mode, C.A.P.E.R is essentially behaving like an electric ventriloquist dummy. The partial manual live operation uses the parallel input for the mouth actuator. The user can plug a microphone into the control board and control C.A.P.E.R's mouth with their voice. The 3 remaining movements can still be operated with the corresponding push buttons, or be moved automatically using the partial manual mode. By flipping a selector switch mounted on the enclosure of the IOCB, the user can activate a subroutine within the IOCB's program. This asynchronously randomizes the head, body, wing, and tail movements, allowing for complete hands-free operation of C.A.P.E.R. The pre-recorded sequence operation allows C.A.P.E.R to be operated like a traditional animatronic using an external playback device. Using any easily attainable digital audio workstation, the user can pre-program a sequence of movements onto their computer using MIDI and transmit the data stream into C.A.P.E.R's UART input. Once a sequence of movements has been recorded by the user, that exact sequence can be played back repeatedly. The automatic live operation allows C.A.P.E.R to listen and respond using a synthetic voice to users with its speaker and move in time with the voice response. Neither the movement nor the content of the voice response given is pre-programmed in this operational mode.
Here is the main block diagram that shows all of the main circuit groups for C.A.P.E.R. The green block represents the low-level computer. All the blue blocks represent the peripheral circuits either at the input or at the output. And the pink block represents the high-level computer that does all the language model processing. All the low-level processing is done on our custom board we call the Input-Output Control Board, or the IOCB for short. This board is responsible for taking all the classes of input, processing and decoding them, and then streamlining the data to a single set of outputs for the relay board located off the IOCB. At the heart of this board, we have the Texas Instruments MSP 430 G2553 MCU. As well as the microprocessor, we have several peripheral circuits that are located directly on the IOCB, including the headers for the push button and the selector switch, the MIDI optocoupler circuit, the headers for the external debugger and programmer, the power supply and voltage regulators on the board, and the voice activation or Vox circuit. Altogether, there are 6 total inputs and 4 total outputs on the IOCB. As seen by the program, you have 4 GPIO-style analog inputs for the push buttons, you have another GPIO-style input for the selector switch, and then you have the UART RXT pin for the MIDI. And of course, the 4 output streams are also configured GPIO pins. The program processes all these inputs at a first-come, first-served basis, and then triggers the corresponding output. When you dive more deeply into the program, you can understand better how this works. The different classes of input are triggered using interrupts. All of the 4 push buttons are located on port 1 and will trigger the port 1 interrupt. All of the data from the MIDI stream will trigger the UART interrupt, and all of the data from the selector switch will then trigger the port 2 interrupt. This makes it easy for the program to decipher which mode the user wants to work in. Here we see the flowcharts for the port 1 and port 2 interrupt functions. The port 1 interrupt function deals strictly with the 4 push buttons when the selector switch is in the off position and nothing is at the MIDI RX buffer. When any of the buttons are pressed, the flag will raise and the program will enter the port 1 function, and that function will scan all 4 of the button inputs to see which ones are pressed. This means the user can press a single button individually or press any combination of the 4 and it will trigger the desired outputs. Although not pictured here, the microphone activation circuit or the Vox circuit shares the exact same GPIO pin as the mouth button, so talking into the microphone will trigger the mouth just like pressing the mouth button. This function will get repeatedly called until all 4 buttons are depressed. In the case of the port 2 interrupt function, this deals strictly with the selector switch. Turning this switch into the on position will leave the mouth completely manual just like the port 1 function, but will automate the head, body, and tail movements. This is done using a counter system, creating the illusion of random movement. This allows the user to then use the Vox circuit and trigger the mouth manually while the rest of the body is automatic, allowing for completely hands-free operation. This function will continue to run until the selector switch is turned off, and then the program will return back to the main. In the case of the UART function, it's slightly different. Whenever a message is received at the MSP's RX buffer, or the UART receive buffer, the UART interrupt flag will raise and the program will enter the handle MIDI function. Using the MIDI standards, this program will then decode whatever message was sent and then activate the corresponding movements. In total, there are 8 possible messages that can be decoded, 4 to activate each of the 4 movements and 4 to deactivate each of the 4 movements. Any message outside of these 8 possible readable messages will be ignored by the program. After each message is received and decoded, and the corresponding output is turned on or off, the function will return to the main until the next message is received.
We considered several different types of motion systems for C.A.P.E.R. Pneumatics were quickly ruled out due to cost constraints. Geared DC motors were ruled out because there is no practical way to control the position without resorting to mechanical limitations. The small plastic gears in these motors are not well suited for stressful applications. Stepper motors are suitable for direct drive applications such as printer carriages and prismatic robotic arm joints, but since all of C.A.P.E.R.'s movements are rotational, stepper motors have no practical use here. Servo motors and solenoids seem to be the most practical solutions for C.A.P.E.R.'s movement, but both involve a compromise. Given the constraints and goals for C.A.P.E.R., it would seem solenoids are the better choice. Servos boast the ability to control speed and position, but are expensive and difficult to implement. Solenoids are cheap and easy to implement, but act in binary fashion, with little to no position control. However, solenoids allow for direct control from the custom IOCB board, and their binary nature allows for a far easier programming scheme with a VRB. There may be some movement inaccuracies, but the compromise in movement accuracy is far overshadowed by the gains of lower cost, near silent operation, ease of control, and a simplified controller design. Ultimately, we went with Exit because this version fits within the size, weight, and power constraints and has the best all-around specifications for the price.
For selecting the MCU, we found plenty of options that all would have been suitable for our project. Due to the fact that we had used it before, we defaulted to using the MSP430G2553. We didn't need all the pins offered by some of the other models, and this model was cheap, easy to use, and through-hole, which is what we wanted. Other models had similar specs, but the MSP430 was the easiest for UART and debugging. When selecting the relay module, we were initially going to go with a switching BJT. However, due to the setup with our plus 5 volt regulator and it being switching, we decided to go for physical relays because their ability to handle more current.
Between the 3 choices of microphones, dynamic, condenser, and ribbon, we chose to use a dynamic microphone due to affordability and the lack of requirement for phantom power. Dynamics have an edge over condensers due to not needing a phantom power supply, and ribbons are far too expensive. The presence of a phantom power supply, especially a cheaper one, would have a negative impact on the noise floor. For the power supply, the Meanwell LRS was chosen over the HRP simply due to the HRP doubling the cost of the LRS. The HRP costs around $50 to $60, while the LRS costs $20 to $30 depending on the vendor. The table compares the 150 wattages, but ultimately we opted for the 350s due to the high current draw from the solenoids. The LRS 350s are essentially a higher power version of the LRS 150s with the addition of a fan in the system as well. We also added 2 12-volt 1 amp power bricks for the positive and negative supply voltages. 1 amp is more than enough for the IOCB and relays since the loads for the bricks do not exceed 300 milliamps each.
The Unified Conversational Pipeline, or UCM, is designed to listen for speech, respond to speech within 3 seconds, and apply movement commands to match speech. For this project, the software choice defined the hardware choice, so it will be discussed first. The framework was selected to be PyTorch, as it is the best out of the 3 that were reviewed in terms of ease of use and power. The model types for the designs are as follows. Transformers for everything. Transformers, it seems, were the best option for all model types. The ASR, the large language model, and the text-to-speech synthesizer. The choice of models are OpenAI's Whisper Small as our ASR, Mistral 7B as our large language model, and Speedy Speech as our text-to-speech synthesis engine. The high computational needs of the Universal Conversational Pipeline, or UCM, require specialized acceleration hardware to run at the required speeds. The final implementation makes use of two distinct pieces of software that communicate via the internet. The Edge submodule, the part of the system that talks directly to the robot body, runs on the Jetson Nano development kit. This dev kit was chosen for its high speed relative to its price. The server submodule, on the other hand, the part of the system that processes the audio into something audible and relevant, runs on an Ubuntu desktop acting as a server running the necessary code. The communication protocol used are the following. The UART protocol was chosen to connect to the VRB to the IRCB due to its simplicity and flexibility. It can transfer MIDI from board to board for the movement commands and allows us to use a USB mic and USB speakers as our audio I/O. The TCP-based OpenSSL was our choice for edge-to-server communication for its high speed and security. The Edge side application works by creating 3 threads: recorder, sender, and receiver. The recorder thread constantly checks the mic signal for a speech-caused volume change. If that change is found, the system records that into a buffer and checks the next signal. Once the audio stops being loud enough to be speech, the system writes the buffer to a file and adds the time-stamped name to a queue. The server polls the queue size. If any names are in it, it will send it via secure copy to the server's input directory and raises a flag for the receiver to try and get the response from the server using the same timestamp signature. The receiver constantly tries to retrieve the appropriate output file. When it succeeds, the file is played via ASLA. The server-side application works by creating 2 threads, input and synthesis. The input thread constantly polls the state of a shared input directory, adding the name of any new files to a shared queue. The synthesis thread constantly polls the size of the shared queue. If any file names are found within, it transcribes the file using Whisper, predicts an LLM response using Mistral 7b, and synthesizes the output audio through Speedy Speech based on that file's signature, and adds it to a shared output directory for retrieval by the Edge submodule.
Let's take a deeper dive at the schematics and circuitry that the IOCB is composed of. Beginning with the power supply, here is a block diagram that shows how the power from the external bricks supplies the voltage to the 3 onboard regulators and then downstream to each of the peripheral circuits. In the case of the -5 and +3.3 regulators, all of the loads that these regulators supply voltage to are ultra-low current, meaning 10 milliamps or less at all times. In the case of the +5 regulator, it supplies voltage not only to the Vox circuit on the IOCB, but a set of header pins allows connection to the external relay board, which is not pictured here in this diagram. Which is why when you look at the schematics seen here, the +5 circuit has a set of protective diodes as well as a VXO chip. This means that this is a switching regulator instead of a linear regulator like the 7905 and the LM1117. Switching regulators are a lot more efficient and are capable of supplying much more current, in this case up to 1 amp, whereas the linear regulators are quite a bit less efficient and are only good for ultra-low current applications. As you saw from the previous slide, each of the 3 regulator circuits have a pair of capacitors. One is shunted at the input and one is shunted at the output. The values of these capacitors are the recommended values as seen in each of the chip's corresponding datasheets. Now let's take a look at the ham radio Vox circuit. This circuit is responsible for converting the language seen at the microphone into a readable pulse signal that is sent to the mouth input GPIO pin. It works like this. The audio enters an inverting amplifier stage with an offset, the second comparator stage, a half-wave rectifier diode, and a filter capacitor. This then enters the gate of an N-channel MOSFET that is shorted between the mouth input pin and ground. It essentially acts like an electronic button. Now let's take a look at the MCU schematic. We use the 20-pin version of the MSP430, and only 14 of these pins are used. 2 are used for power, 2 are used for debugging, and the remaining 10 are used for the 6 inputs and 4 outputs. All of the MIDI devices that you use with this have to pass through the MIDI optocoupler in order to connect to the MCU. This device has 2 main functions. Mainly, it isolates the ground plane of the IOCB from the local ground of the external device. The second main function of this circuit is to step down the standard plus 5 volt square wave to a more usable 3.3 volt square wave that the MSP is capable of handling. The last part of the schematic I'd like to show is the reset circuit. This is simply a 10 kilo ohm pull-up resistor from the reset pin to the 3v3 supply for the MCU.
Our second PCB layout is shown here. Our first edition of our PCB was so heavily tweaked when we met with Dr. Weeks that it never made it to production. When constructing this PCB, 6 out of the 7 circuits worked perfectly. However, due to a few wrong connections and an incorrect footprint for the transistor, it led to the Vox circuit being shorted and not working properly. These boards were kept as backups for our B3, which is what we produced 2 weeks later. This here is our final PCB layout and was imported and brought in last week. Instead of having the assembly done by JLC PCB, we just got the boards made by them and soldered on all the components ourselves. Other notable changes for this board are that we used a 3v3 plane. If you look on the right there, you can see the change in the 2 different greens is the 3v3 plane on the right, and the left half being the ground plane. This made a lot of the connections on our board easier. This time as well, to avoid the incorrect connections that we had on the second version, every circuit had its own designated space in the board, and we have now manufactured 2 successfully working versions of this board. The chassis was 3D printed and will be used to house the important circuit boards, power supply, anything else deemed necessary. It can also store some of the wiring that could be seen as obstructive to C.A.P.E.R's realistic display, and the dimensions of our chassis are 9.5 inches by 9.5 inches by 5 inches. C.A.P.E.R's initial frame can be seen on the left here, and that was used to showcase exactly the 4 movements and try and figure out what angle of change could be implemented when we tried to get it moving. All our prototyping was done via breadboarding, which had us in the lab testing the voltages coming from our regulators and if the Vox circuit was responsive to audio input. And then before installing a voice, we were able to get the LLM and text-to-speech models working, and we're having complete conversations with C.A.P.E.R. Our final prototype can be seen below. The design of C.A.P.E.R's shell is purely cosmetic and has no impact on the electrical system, which works flawlessly. C.A.P.E.R has the 4 distinct bodily movements that we were intending to put in there, as well as multiple input modes, being the selector switch, the input buttons, the Vox circuit, as well as AI compatibility that we were hoping to put in. The AI is live and, despite sounding like a nice sounding Frenchman, works very well. C.A.P.E.R performs all of the functions as specified by our 120-page document and in our engineering specifications. Given that our team had 3 EEs and 1 CPE, there was a lot more collaboration than a typical senior design project. Most of the AI was handled by Paco, our computer engineer, but the rest was split pretty evenly among the other 3 EEs, but our work documentation is below. The following is our budget for this project, and as you can see on the second slide, we came in significantly under what we were aiming to go for. As far as what we would do differently when doing this project again, the main thing, and by far the biggest thing, is that we would assemble all of the PCB in-house this time. When we ordered our initial PCB from JLC PCB, there were a lot of just incorrect values in some of the resistors that we asked for, and there were some scratches on the boards. So overall, it was much more reliable and much better if we could do it on our own and test each circuit as we constructed it. We would use more up-to-date solenoids. Just the ones that we have are a little older, sometimes seem a little faulty, but it doesn't really affect most of the electrical design. They still work at about a 95% rate. And then the last thing, we're not mechanical engineers, but if we could work around the physical construction of the bird so it can support more weight, it would help for us to be able to make it look more realistic because we could add more cosmetics. For our future enhancements and what we could continue to add to C.A.P.E.R, we could fine-tune C.A.P.E.R's voice so that she sounds more realistic. We say she, but she currently has the voice of a Frenchman. So there were a lot of other options we could have implemented, but this one was the cheapest and the easiest and was what the system recommended. We could add sensors to create a more realistic bird that could have other kinds of inputs, like it could tell when someone's talking to it, it could tell when someone's walking by. So that would help add to the realism, if it's reactive to its environment and not just to buttons or some kind of specific input. And then the last thing would just purely be cosmetic, but giving her a finished body, making her look a lot more like a real parrot, or whatever we were going to shape them up for in the theme park or wherever they would be implemented.